In this video, we're going to take a look at a sample of problems from section 15.1 of College Prep Math. This module is on system of equations, and 15.1 is an introduction to that material. The first kind of problem that you'll have on the homework, and I just kind of picked these at random. I don't know how representative they are of the other problems in the homework. But the first set I noticed was about understanding what a system of equations is. So they're giving you two equations here, each equation having two variables. So we have 3x plus 5y equals negative 11. We have 4x plus 2y equals negative 10. What we're looking for is an ordered pair, an x and a y value together, that works in both equations at the same time. So it doesn't really say that in the directions, but when you're being asked to find a solution to a system of equations, you are looking for an ordered pair that works in both equations simultaneously. And you're going to learn different techniques for doing that throughout the module. But for this first type of problem, just to make sure you understand the concept of what you're actually looking for, they're giving us an ordered pair and they're just asking, it's a yes or no question. Is this ordered pair a solution to the system of equations? It's a solution if it works in both of them. So we have to check both. And we will be plugging these numbers into both equations. If it works in both of them, then yes, this is a solution to the system. If it doesn't work in both, meaning if it works in neither one, or if it only works in one but not the other, that's still not good enough. It is not a solution to the system of equations. And so that is how you will answer this question. So it's given to us as an ordered pair. That means the first number is the x value, that's the x coordinate. The second number is the y value. So this is just a really convenient way, instead of having to write this out. Let x be negative 2, let y be equal to negative 1. They're saying all of this by writing it as an ordered pair. You know the first number is x, the second number is y, so they don't have to actually be explicit about that. All right, anyways, we want to check in both equations, and I kind of want to build up the suspense here. I don't know if this actually works or not. So let's start with the first equation, because just because it works in one doesn't mean it's a solution. You have to check both. Now, if you check one and it doesn't work, then right away you know it's not a solution. So I don't want that to happen. So I'm trying to think ahead, and I think we'll be okay if we go ahead and just go with the first equation. So 3x plus 5y equals negative 11. We are going to plug in negative 2 for x, and we're going to plug in negative 1 for y. Everything else is going to stay the same, so we'll still have 3 here, plus this will still have a 5, equals negative 11. Right? I'm just basically copying the equation down on the next line, but replacing the x and y with these two numbers. And then we'll simplify. So 3 times negative 2 is negative 6. 5 times negative 1 is negative 5. We get negative 5 plus negative 6. I said that backwards, but same difference. We get negative 11 when I add those two together. Negative 11 does equal negative 11. So this ordered pair does work in the first equation. It's a solution to the first equation, but that doesn't mean it's a solution to the system of equations. So there's layers here, right? So there's solutions to the individual equations, and then there's the solution to the system of equations that we're looking for. So this is a solution to the individual equation, but I don't yet know if it's a solution to the system because I still have to check the second equation. So I'm sorry I didn't do a good job circling that, but let's check the second equation. So I'll copy it down here. We have to make sure this set of numbers also works in the second equation. And so I'm going to plug in negative 2 for x. I'm going to plug in negative 1 for y. I'm sorry I didn't color code it as nicely this time, but I think you get the idea of how to plug in a number for a variable. And then we're going to get negative 8 here when I simplify this, plus negative 2. And when I add those together, I get negative 10. That's exactly what I have on the right-hand side. And so it also works in the second equation. And so because it works in both, yes, negative 2 comma negative 1 is a solution to the system of equations. And so on Math Excel, you'll simply answer yes. It'll be a yes or no option somewhere on the screen. You'll say yes, this is a solution. Let's take a look at the next example. Okay, so in this example, they're giving us a system of equations. We have x plus y equals 8, and we have y minus x equals 8. But this time, unlike the last example, they are not giving us an ordered pair to test out. And so this is not a yes or no question. This is, you're on your own. You figure out what the solution is. We're not going to give you a pair of numbers to try. You're going to have to find it for yourself. And so here we're going to learn our first technique for finding the solution to a system of equations, which is by graphing. And so they have the graph set up here. I zoomed in to make it a little bit easier to see on the screen. But then it kind of messed up the graph, like it put these bars on there. So I tried to scroll it where I thought the numbers were going to be relevant. So hopefully it'll work out okay. And so you're going to have to think back to a previous module. I find a lot of students when they get to module 9, I think of it as one of the easier modules, especially near the end. But some students really struggle with it, and it's really this part that they struggle with the most. It's the graphing, because it's been a few modules since you did any graphing. I'm trying to think when it might have been, module 5, module 6 maybe. And then you might have learned it well enough to get through that module, and then you didn't see it for a while, so you just kind of expunged it from your memory banks. And so you want to make sure you bring it back in because you're going to need it for this module in this section of the homework. And I think there's 1 or 2 more sections where you're going to have to do a little bit of graphing. And so this is a linear equation. And so when we graph it, the graph will be a straight line. We can recognize that's going to be the case because the equation fits this formula here. Ax plus by equals c. Alternatively, if it fits this formula, it's also going to be a line when you graph it. And so you might also see equations written like this. Again, it's going to be a line when you graph it. And there's different methods for graphing a line, but they all boil down to one thing, which is you have to find 2 points. Once you have 2 points, you connect those 2 points with a straight line, if you know the graph is supposed to be a straight line. And so I just need to get 2 points out of this equation. And when it's written in this form, I think the quickest way, especially if the numbers are cooperative, which they will be here, is to find the x and y intercepts, because you really can do this mentally once you've practiced it a few times. So the x-intercept, which again is something else you probably learned several modules ago, you find this by setting the y-coordinate equal to 0. You set y equal to 0, plug that into the equation, and then you let the equation tell you what the x-coordinate has to be. So anytime you're finding solutions to an equation like this, when there's 2 variables, you get to pick one, but the equation tells you what the other one has to be. So we're picking y in this case, then the equation will be in charge of telling us what x is equal to. And so plug that into the equation. And what's great about intercepts is that you're plugging in zeros. And when you plug in 0, things just kind of go away, and it makes the equation a lot easier to manage. And so when we plug in 0 for y, basically that just goes away, and we just get x is equal to 8. And as I mentioned, you really can kind of mentally see that happening. You take 0, you plug it in for y, that term will just disappear, you get x is equal to 8. So I don't have to do all this writing, I can kind of work it out mentally. All right, and so we get 8 comma 0, which would be this point right here. It's on the x-axis because it is an x-intercept, and that's where that point should be found. Okay, now for the y-intercept, we're going to do the same thing, except reversed. Right? We're going to plug in 0 for x, and then let the equation tell us what y is equal to. So I'll take my equation, x plus y is equal to 8, plug in 0 for x, that just goes away, and we get y is equal to 8. Again, you can kind of see that happening mentally, right? When you plug in 0 for x, that term goes away, you get y is equal to 8. And so you get 0 comma 8, which is a point on the y-axis, and it's located I was just barely able to fit it, but I kind of saw that was going to happen, and so I made sure to try to get all the 8s in the screen at the same time. Once you have your 2 points, you connect them with a straight line. So we will go ahead and do that. I guess I'll stick with red as the color. And thankfully this program has a line drawing tool. It's a little off the mark from where I drew my point, but it's actually right on the mark as far as hitting the 8. And you saw it didn't really have a lot of tolerance there, like it would jump pretty far. So thankfully it fit right where it needed to go, which is right here. All right. So that is the line for this equation here. And what you need to remember for this whole process to make sense, now I could just tell you, do this and here's where you find your answer, but I want you to understand why this process works, why it finds you the answer that you're looking for. On this line is where x plus y always equals 8. Every point on this line is a solution. Whoops, I hate when I do that. Is a solution. Sorry, I moved the recording area. I don't know what that looks like. I've done that a couple times, but I've never watched to see how it shows up in the video. So hopefully it's not too disorienting. What I was trying to do there, and it kind of started to do that, is I wanted to circle this. So let's try that again. All right. Every point on this red line is a solution to this equation. Now remember from the previous example, what we're looking for is an ordered pair that is a solution to both equations at the same time. These points are only solutions to this equation. So I don't know which of these points would be a solution to my system until I consider the other equation, which I'm about to do in just a second. All right, so remember, every point on this line is a solution to this equation. Every solution to this equation is a point somewhere on this line. That's the connection between graphs and equations. So for example, like I mentioned, every point on this line, the x plus the y is equal to 8. So if I take like this point, it's 4, 4. 4 plus 4 gives me 8. If I take this point, it's 2, 6. 2 plus 6 gives me 8. If I take this point, it's 5, 3. 5 plus 3 gives me 8, right? That's the pattern for every point on this line. When you add the x and the y together, it will always add up to 8. Right. Now, let's do the other equation. This time, I want you to try to do this one. Find the x and y intercepts and see if you can do that mentally without having to write out the work. All right, so pause the video, decide what you think the x and y intercept should be, and then resume the video to see if you came up with the right idea. All right, so for the x-intercept, what you should be coming up with is, this one's a little bit tricky. We didn't have this issue over here. You plug in 0 for y, just like we did over here, right? Plug in 0 for y. When you plug in 0 for y, that goes away, and you get negative x. So don't forget about this minus sign. Negative x equals 8. To solve that for x, you divide the negative to the other side. So if we divide the negative to the other side, we'll get x is equal to negative 8. So you should be getting negative 8, 0, which is right here. All right. For the y-intercept, this one should go a little bit more according to what you saw over here. You will be plugging in 0 for x. So when I plug in 0 for x, that term goes away. We get y is equal to 8. So you get 0, 8. So that makes it pretty easy to see. Of course, I thought maybe we'd have a little bit more to look at here, but you can see exactly, I guess I'm skipping ahead of myself because I haven't told you the punchline yet, but let me just get to that first and then you'll see what I'm talking about. So now let's draw a line because we're not done. We need to graph this equation. We have 2 points now. It just so happens to be the same point we had from the other equation. I connect them with the straight line. Again, it would really go past that point, but I've run out of room on my screen. And it would go past this point as well, which that looks a little disjointed. Let me see if I can line that up. It doesn't want to let me. It looks like it's a little bit, how do you say, the tolerance there. There's not a lot of flexibility. Okay, that actually doesn't look too bad. Okay. It seems like you can either pick this spot or this spot, but nothing in between. That's what I'm trying to say. Anyways, this line, every point on this line is a solution to this equation. Right? So, and this has the pattern that if you take the y coordinate minus the x coordinate, it always equals 8. Right? So if we take like this point here, for example, this is negative 1, 3. Sorry, why am I taking this point? It's not on the line. I'm being silly. This point right here, right? It's negative 1, 7. And so if I plug in negative 1 for x, 7 for y, and I subtract those, minus the negative becomes plus, I get 7 plus 1, which equals 8. Right, so that's the pattern. For every point on this line, the y coordinate minus the x coordinate always equals 8. Every point on this line is a solution to this equation. Every point on this line is a solution to this equation. I'm looking for a point that is a solution to both equations at the same time. And that point will be where the two lines cross each other, which will be right here. Right, so this point where, again, normally it's not going to be one of the points you're finding for your graph, but that happened in this case, right? It's this point here at 0, 8. 0, 8 is on the red line, so it's a solution to this equation. 0, 8 is on the green line, so it's a solution to this equation, which means it's a solution to my system of equations. Something else you can learn from this, understanding this process, is that if your two equations are linear, if they're both lines when you graph them, two lines can only cross each other at one point. So that tells you that these system of equations can only have one solution. So going back to this, these are linear equations. So this system of equations can only have one solution. And so this is the only one, right? Once we confirm that this is a solution to this system, it's the only solution to this system because these are two lines, and two lines can only cross each other once, right? With one silly exception that maybe we'll talk about here on a later example. All right, so I have two more examples, again, just kind of sampling the different types of problems. I only saw one other type of problem, but I thought I would do another of this graphing type just to give you an idea of the difficulty level that might be involved. So I thought this was a good example because it has like a mix of different types of equations, and the numbers are bigger. And so for this one, we're gonna solve it the same way. We're gonna graph both of these equations on the same Cartesian coordinate system and look for where the two lines cross each other. That'll be my solution to my system of equations. They're both linear again, right? Because this fits the form y equals mx plus b. So this is a line. And this time, though, instead of using the x and y intercepts like we did on the last example, and like we're going to do with this one here when we get to that, this one, when it's set up in this form, the quickest way to get 2 points is to use the slope, right? So m is the slope, which in this case is -1/4, and b is your y-intercept. So you don't have to actually calculate it like you do when the equation looks like this. It's actually just read directly off the equation, right? This number, -5, that's going to be your y-intercept. And so that gives you a point, right? So that's 0, -5, which is going to be on the y-axis right here. The slope gives you directions for finding a second point. So the slope is not a point in and of itself, but it's like the example I've given in class occasionally is it's like a treasure map, and it's telling you, like if you think about like traditional treasure maps, you go 10 paces north, you go 12 paces west. That's kind of the way treasure maps have been shown in movies, right? I mean, I don't know if there's ever been treasure maps in reality that function that way, but in Hollywood, that's the way treasure maps are described, right? Well, that's how the slope works. The slope is the rise over the run. The top number tells you how far up or down to go, so that's north or south. The bottom number tells you how far east or west to go, that's left or right. So the top number here, and there's a negative sign, which we need to take into account. I usually apply it to the top number, but you have to pick which number gets the negative sign. You can put it with either one, doesn't matter. I let the top number be negative. And so this is going, because it's a -1, this means we want to go down 1 from the point that we already have. And because this bottom number is positive, we are going to go to the right 4. Right? So again, the bottom number is going to be left or right. Left is negative, right is positive. So we will go to the right 4 from this point. So I have a set of directions I'm going to follow. I'm going to go down 1 and then to the right 4, which is going to lead me to this location here. And so I mark a point there. Right, so wherever you land, after you follow this set of directions, wherever you land is another point on the line, so you go ahead and bubble it in. Now I have 2 points, and I could keep going. I can make more. I just go down 1 to the right 4 again, and I get another point. Right, and you can just keep doing that and make as many points as you want. But 2 is all we really need to draw this line. So let's go ahead and connect these 2 points with a straight line. I should connect all of the points that you're drawing out, by the way. And it's going to go in both directions. I'm going to try to line this up and make this go the way it's supposed to. So if I went up 1 and to the left 4, sometimes that's another way you might handle this, is If you don't have enough room to go this way, whoops, sorry about that, you could go backwards. You could go up 1 and to the left 4. So it's by switching the negative sign. You can think of this as positive 1, think of this as negative 4. That's up 1 to the left 4. It gives you a different point, but it creates the same line. Right? And so remember, this line, every point on this line is a solution to this equation. Right? Now let's graph the other equation. We have 6x minus 4y equals 48. I'm going to use my shortcut without writing a lot of stuff down because, this video is already getting a little bit longer than I intended. And so let's do the x-intercept first. And let's try to work this out mentally, right? So the x-intercept, you plug in 0 for y. If I plug in 0 for y, that term just goes away. I get 6x is equal to 48. I solve that for x by dividing 6 to the other side. And so we'll get 48 divided by 6, which is going to be 8. Very good. And I kind of meant to erase my marks first before I put the 8. Okay, let's do that. Now, for the y-intercept, we're going to plug in 0 for x. That's going to make this term go away. I'll have negative 4y equals 48. To solve that for y, I divide the negative 4 to the other side. All right, so it's going to look like this. So with this being 0, 6 times 0 is just going to be 0. 0 minus 4y is just negative 4y. So really that term just literally disappears. So just in case my verbal description is a little bit hard to follow, let me at least do one example of this. And so you would get this. When you plug in 0 for x, it results in this. Then to solve that for y, you divide negative 4, right, which is what I was saying a moment ago. And you get negative 12, which is kind of a big number. Again, I tried to make sure the numbers would be visible here when I captured this problem for to work on. So we have, I should have done this point already, 8 comma 0, which is right here, and then 0 comma negative 12, which is right here. And that gives me 2 points, and 2 points I can graph the line. And it's going to go like this. So this time, unlike the last problem that we did, the point where they cross is not one of the, well, I guess it was one of the points I actually found. Well, it was one of the points I found for the first equation, but not for the second one. So like I said, it's pretty uncommon that when you're finding your points to graph, that you find where they intersect in those points. And so we see that here, that, the 2 points I use here, 8 comma 0 and 0 comma negative 12, don't match the 2 points I did over here, right? So where do they cross? They cross at this point right here. Right, whoops, I'm still doing the line drawing tool right here. Okay. And so we want to get the ordered pair for that point. It's going to be at 4. That's the x coordinate, right? Make sure you put x first. 4 comma negative 6. That's where they cross. That point is a solution to both equations at the same time because that point is on both of these lines. It's on the red line, which makes it a solution to this equation. It's on the blue line, which makes it a solution to this equation. So it solves both equations at the same time, which means it's a solution to the system of equations. So we have 4 comma negative 6. That's what you would type into MathExcel. Now to get to that point where you type that in, you have to do the graphing first. So MathExcel makes you draw the graphs, and then once you have the graphs, then you can type in your answer. There are other methods for solving these system of equations that you will learn in later sections. And you might already know some of those methods, and so they don't want you to skip the graphing and use one of these other methods that you're going to learn that don't involve graphing. They want you to understand the graphing aspect of these problems first. All right. So there's one more example I wanted to look at, and these questions are kind of weird. I don't have these type of questions in my intermediate or college algebra classes that are set up this way. The content is there, but the way the problem's set up is a little bit weird. It's a little bit awkward. So this time it's without graphing. Answer the questions for the following linear system. And what they're asking is, what type of system do we have? Is it dependent? Is it inconsistent? Or is it neither? So these are two special cases that can occur with a system of equations, which we have not experienced yet. All of the problems we've done so far have been what we call independent system of equations. So if you solve it and you get a solution, that's an independent system. That's the normal outcome that happens 95% of the time. But there are certain systems of equations that don't follow that outcome, and they don't work out exactly in the normal way. And that's what these two cases are. So an inconsistent system is one that has no solution at all. Right, so it is possible that you solve a system of equations and you find there's no solution. A dependent system, I know I said that with lines there's only ever one point where they could cross, but a dependent system has an infinite number of solutions. And there's only one way that can happen when you have just two variables, and it's a really silly outcome, which in fact I believe is the case here. And so the way you know which one is the case, and so neither I guess would be the case where it's independent and you get a solution. So if you get a solution, in the case of two variables, well, I guess maybe not even in all cases, but in the case of linear equations with two variables, if you get one solution, it's independent. Right, so that's how you know it's neither, because it's the independent case and you get one solution. And that's been all the examples we've done so far. How will you know if it's inconsistent? If the lines are parallel. There's two lines that are parallel. And the reason that means there's no solution is because, remember, where do we find our solution to the system of equations? We find that solution where the graphs cross each other. But parallel lines would not cross each other. So if you have two lines that aren't crossing, that means there can't be a solution, because where they cross is the solution. If there's no crossing, there's no solution. And so parallel lines are lines that don't cross. So if you have parallel lines, that means there's no solution. Now, how can you tell if you have parallel lines without graphing? You'll know they're parallel if the slopes are equal. So if the slopes are the same, you have two lines that are parallel. That means there's no solution. For infinitely many solutions, what happens here is you have the same equation twice. It's a really silly, I don't really like this example very much, because to me, if it's the same equation, it's not really a system. It's just one equation. You're just writing it twice. But the concept is still worth being aware of, because it becomes much more interesting when you have systems of equations with three variables. Then the dependent systems are really pretty interesting. And it's not because you have the same equation over and over and over. But for two variables, the only way this will come about is you have the same equation twice. Right, at least for linear equations. And so that means when you graph it, there's just one line. And so if you only have one line, you have infinitely many solutions. It's a dependent system. All right. Now, which is the case here? How could we tell? Well, the way you could tell if there's two lines or one line, because here's the problem. When you look at the slopes, if you only have one line, they'll both have the same slope because it's the same line. If you have parallel lines, they'll have the same slope. So you can't tell just by looking at the slopes. You have to look at the slopes and also whether the lines are going to be distinct from each other, or if they're going to be the same line. So in this case, what I would recommend doing is maybe solving both of them for y, because if you want to look at the slope, you can find the slope by solving the equation for y, because then you get y equals mx plus b. The number in front of x is going to be your slope. And then from there, you can tell if they're parallel. And you can also tell if it's really the same equation twice, because if you solve both of them for y and you get the same equation both times, you have the same equation twice. That's just one line. It's going to be dependent. So let's take both of these equations and solve them both for y. That's really going to be the best way you can approach this problem. So when you get to the end, and there's a lot of them. I was looking and there's like multiple of these. I feel like it goes a little bit overboard. But the best way to handle these problems is to solve both of them for y. And if you get the same equation twice, it's dependent. If you get two different equations, but the slopes are the same, it's inconsistent. If you get anything else, it's neither, which means it's independent and there's just going to be one solution to that system. So if the slopes are not the same, if the equations are not the same, then it's going to be neither. All right, so what happens here? We have x plus 5y is equal to 0. So we want to solve this for y. So we want to move everything else to the other side. So I'll subtract x to the other side. I get 5y is equal to negative x. I divide by 5 on both sides. And I get y is equal to The way I would want to rearrange this is whenever you're doing linear equations, you want your equation to look like this formula, which means you want the x to be separate from the number so you can get a clear sense of what the slope is. So I really want to write this x off to the side of the fraction. So I'm going to put the x off to the side. When I move the x out of the fraction to the side of the fraction, it's going to look like it's blank here, but really what you have here is an invisible 1, right? There's a 1. This is 1x. We just normally don't write the 1, but if you're going to move the x off to the side, the 1 has to become visible. And so you'll have a 1 left on top, you still have the 5 on the bottom, and it's negative, right? And so this is the equation. This is the equation solved for y from the first equation that I was given. Let's do the same thing. I do a bad job of putting boxes around things. Okay, let's do the same thing with the bottom equation. Solve it for y. This one's going to be a little bit easier. You just have to divide 15 to the other side to get y by itself. So I'll go ahead and finish that over here. We're going to get y equals negative 3x over 15. I'm going to do the same thing. I'm going to move the x off to the side. So we get y equals negative 3 over 15x. And as always with fractions, this is a good reason why you always want to do this. You need to reduce. And so we reduce this fraction, it reduces to 1/5. And so you see we get the same equation twice. They look different when they're given to us, but when I solve them both for y, I realize this is actually the same equation both times. They just were written a little bit differently. And so the correct answer here is dependent, right? So we got the same equation twice. This will be dependent. So for part B, is the graph a pair of intersecting lines? That would be independent. You get one solution from that. A pair of parallel lines, that would be inconsistent because parallel lines you would have no solution. Or is it just one line? In this case, it's just one line because we got the same equation twice. That's just going to give me one line when I graph both of them. It'll give me the same line twice. So there's just one line, which is always going to be the case when it's dependent and it's linear equations, which is all this module is about. Does the system have one solution, no solution, or infinitely many solutions? Well, if it's dependent, there's infinitely many solutions, so you'd answer infinite here. Sorry, I'm kind of jumbling my words. So sorry, that video took like half an hour. I thought it'd be like maybe half of that time, so I'm sorry if I got a little bit too verbose there, but hopefully I just did a random selection of problems of each type, I hope. I hope I didn't leave anything out. And I hope that gives you an idea of how to approach these problems. And if you're one of my students and you still have questions about this material, please reach out. Thank you for watching.